Hello, good morning, everyone. Welcome back to the OpenShift TV Coffee Break. My name is Natalia Vinto. I'm product manager for the OpenShift TV, and today I'm very happy to have some special guests. I'm going to introduce our special guest in a second. Before doing that, I'd like to remind you in the chat that if you have any question, if you want to say something, please use the chat and we'll bring the question to our super special guest. But I'm going to introduce them right now. So welcome, Kate. Welcome, Will, to the OpenShift TV Coffee Break. How are you today?
Yeah, really good. Thank you. Happy to be here.
Yeah,
All
great.
right.
Thanks for having us.
Yeah, thank you. Do you want to first of all, I love this show because this episode is going to be about quantum computing. So I'm really excited about it. And if you were wondering why quantum computing now and what it means with OpenShift, we're going to discover this in a moment with our super special guest. But hey, Kate, Will, do you want to introduce yourself to our audience today?
Sure. Yeah, I'll jump in first. So yeah, lovely to meet you all. I kind of work in two roles actually. So I work at IBM as a developer for IBM Quantum. So I develop part of our software stack, which is called Qiskit Runtime, which hopefully we'll have a little bit of a chance to talk about later. But then I also lead the global team for the technical ambassadors, which are essentially people that speak directly to clients about the impact of quantum computing and the different applications and what it means for every industry. So that's kind of the two parts of my role. Will, do you want to go next?
Sure. Yeah. So I work in the infrastructure team of quantum computing. So we do a lot of different things, but it's everything from patching Linux servers through to cloud things with OpenShift, and a real wide variety of tasks. And I'm also a quantum ambassador, which means that I get to come and do things like this, which is great.
Awesome. I like this ambassador. So this is a team going into accounts and kind of evangelizing quantum computing and updating with the state of the art of quantum.
Yeah, exactly. So we do lots of like sort of client outreach to help explain what is quantum if people are kind of at that stage. So we call that quantum tourism. So if you're just really interested in finding out more, then we're happy to sort of come either client site or online to help with sort of client outreach there to help with understanding. And that kind of goes beyond that as well to like university groups, school groups, anyone who's interested. And then Will and I can also come in and talk more specifically about software, about applications, about industry impact and different things as well. So it's a really cool team of people.
Wow, I love it. Yeah, and I think we are all interested on being, those quantum tourists, as you mentioned. Could you give us, Kate, Will, could you give us a quick update of what's the state of quantum computing? Quick preamble. I met Kate in a conference in Luxembourg. We've been at the IBM booth and we were talking about quantum developers with quantum. That's why we started, hey, why don't we do a show about it? So I wanted to share this with the audience. So what's the state today about quantum computing?
Yeah, sure. Will, do you want to take this one or would you
Yeah,
like me?
happy to take this. No, happy to take this. So at the moment we're in early research stages of quantum computing. We've come an incredibly long way. So IBM, we put a quantum computer on the cloud for the first time in 2016. But that was quite a small quantum computer. It was very small. And we're in what's called the NISQ era of quantum computing at the moment, which stands for noisy intermediate scale quantum computing. And this means that we have some limited quantum computers that can do interesting things. We can do really interesting experiments on them. But at the moment, we're not at the stage where there are problems that quantum computers can solve that classical computers can't solve. So we're really in like this research stage, and it means that our quantum computers are quite error prone. So we need to do lots of adjustment for these kind of things. And so that's where sort of the whole quantum computing field is. And there's lots of different ways of making quantum computers that are all still in the running at the moment. And there's lots of different ways of doing it. And at IBM Quantum, we use a thing called superconducting qubits. So this is like a specific qubit technology. It's a specific way of making a quantum computer. And originally in 2016, I think it was a 1 or 2 qubit machine that they put on the cloud. So it's sort of equivalent to bits. It's an incredibly small computer. You can't do much with it, but it was like a good proof of concept. And this year we released our 433 qubit machine. So we've come a long way since 2016. And then we're hoping to scale further. I can talk a bit more in detail about that later. But hopefully that gives you sort of a rough idea of where we are.
Yeah, I can add to that a little bit if we have time, Natalie.
Sure, please.
Yeah, so for example, what Will mentioned there, so I think like one easy way for me to sketch it out in sort of timelines, because I think this kind of helps, is Will mentioned this NISQ, or noisy intermediate scale era of quantum computing. So that's kind of like the first stage, and we're still there. We're still in that sort of early, like really cool research and development stage, and things are still sort of maturing, and people are still sort of understanding where the application areas are and where the technology is going and what kind of technology might actually win out in actually building this sort of universal quantum computing goal that lots of these companies like IBM are working towards. And then what comes after that is this era of quantum advantage that sort of Will alluded to there, which is when we see this significant practical benefit over and above what we can achieve with any classical supercomputers available today. And I think part of like really where we are today is we're at the cusp between those two stages. And the stage after that is fault tolerant quantum computing, and that's going to be sort of filled with engineering challenges, scientific challenges. Sort of the physics theory is fairly sort of understood at this point, but the engineering challenges that we're going to be sort of facing when we try and build this to scale so that people around the world can use it, that's sort of going to be sort of something we're starting to experience now, but we don't even know what the extent of the questions we have to ask yet. So it's really exciting that every year we have this Quantum Summit conference, which is where we release all of these announcements. Like Will mentioned, we have a 433 qubit quantum processor available today. That's the largest available in the world. But we also demonstrated things in sort of terms of speed and quality of our quantum processors as well. So we have this metric called quantum volume, and we managed to demonstrate a quantum volume metric of 512, which means our quantum processors are really high quality. They're also obviously still error prone, like Will mentioned, but this is just a way to gauge against sort of different market players where we are on the scene. And then the sort of final announcement that came out of Summit was this metric of speed. So we've defined that as a metric called CLOPS, which sounds a lot like flops, and that's for a reason. So rather than floating point operations per second, we're defining that as circuit layer operations per second. We managed to demonstrate a CLOPS metric of 15,000 on one of our Falcon processors. So these are the sorts of metrics we're getting to today, and hopefully this brings us closer and closer to that barrier I mentioned where we will reach quantum advantage sometime in the next few years. And I've just sent you a link, Natalie, of the Quantum Summit sort of website, so people can visit that if they want to see what other announcements are sort of representing where IBM Quantum are today.
Wow, that's lots of update. I'm really excited. I had to have my coffee shot for the coffee break, to digest all this. But hey, Kate, I just shared in the chat the link you gave me. So the summit, it's an event made by IBM to showcase what the state of the art of quantum, right? And when was this? Is it already happened, or it will happen this year?
So they happen November each year. So the last one was November 2022, and that's when we released all of these sort of scale, quality, and speed metrics, and all of our software announcements as well. So you can hopefully find more updates on that website.
Cool. Thank you for sharing it. And I have already thousands of questions, but hey, in the chat, people attend. If you have any question, please send right in the chat. We will bring them. We're touching now, I think, more the theoretical part for quantum. And I would like to ask you two things. One is, for the audience, maybe it's not really aware about quantum. So could you explain a little bit what is a qubit and why it's important to have? You mentioned some numbers of qubit before, right? So why it's important to have those numbers of qubits?
Yeah, of course, I can take that one. So generally, if I sort of start with what is quantum computing in sort of a sentence, the sort of main thing that I try and hit home with people with for this, because it is like if you try and Google what is quantum computing, you can get all sorts of like really, really complicated physics textbooks and really, really sort of convoluted information that's quite hard to digest. So if we kind of bring it back to what's something that most people can understand, we see that, so basically quantum computing represents a new way of information processing that will help us to tackle problems that are considered today to be classically intractable or impossible to solve with even the world's most powerful supercomputers. So that's how we sort of broadly define quantum computing, as a way of attacking problems and exploring problems in a way that we haven't previously been able to do. And that's using and being able to use these fundamental principles of quantum mechanics, which are terms you may have heard of, like superposition and entanglement. And don't worry, I'm not going to bore you with trying to explain what those terms mean. But more importantly, what those concepts bring us is the ability to create problem spaces, or state spaces as we call them, which we can think of as kind of like equivalent to a laboratory environment if you're a scientist, or like a development server if you're a developer. We're creating these problem spaces, which are places that we can try out problems, so similar to that lab or dev end that we're sort of simializing to there. And in these problem spaces, they have more state dimensions than I can possibly begin to describe to you. So every time we add one qubit, which I'll explain in a minute what that is, to our quantum processor, the number of state dimensions that we can explore at any one time in this environment, in this lab environment that I'm describing, it scales exponentially. And that's an incredible thing to try and even that one concept to wrap your head around is huge. So that means that problems that are actually really, really difficult to solve in lower dimensions of space, we can actually explore those same problems in higher dimensions of space. And suddenly those problems can suddenly become a lot easier to solve. And those types of problems are things like optimization problems, simulation problems, and machine learning problems. So that's broadly like the sort of definition of quantum computing that I give. Try not to get too hung up on superposition and entanglement. If you've tried to read about those things and they've gone way over your head, think more about what those concepts bring us, which is the ability to build these really, really complicated spaces where we have access to more dimensions than well, even with a few hundred qubits, you can access more dimensions than there are atoms in the observable universe. So a huge number of dimensions is what I'm talking about here. So what is a quantum bit or a qubit? That's our unit of computation. When we say we have a processor today of 433 qubits, that means that those physical devices that Will mentioned earlier, those superconducting qubits, we have 433 of those currently hand-placed onto a processor that's about the size of my hand. And each of those different sort of qubits on that processor are either physically entangled with other qubits on the chip. So we have these like actual physical links that actually entangle one qubit to another. And between those 433, we can actually impose states of superposition and entanglement to create these problem spaces that I described. So hopefully that's a little quick introduction to help everyone get on the same page about what we're doing. Will, is there anything you want to add?
No, that was good. That sounded excellent.
That was pretty good. Thank you for this great explanation. It really helped understanding the value. What is a qubit? What are the underlying physics? You mentioned superposition. You mentioned entanglement, and then what the qubit could do. Work on a multi-dimensional, so convert problem in and try to solve them in multi-dimension. So to this point, I was going to ask you. So what class of problem can quantum computing solve? I don't think, maybe can quantum solve all the problems, or it's just some subset of problems?
No, that's a really good question. So, for example, the main problems that we're looking at with quantum are very specific ones that satisfy a strict set of sort of predefined conditions that mean that we can actually encode the problem on a quantum computer, because that challenge in itself is quite difficult. And it does therefore mean that the actual encoding of the problem is hard, but also from like a theoretical perspective, there's only a handful of problems that we would look to solve with quantum computing. And even in this era of quantum advantage that we mentioned earlier, we would never expect to see classical computing rendered useless. There's at least as many problems that are impossible for a quantum computer to solve as there are for a classical computer to solve. So really, it's a small set of problems that we're focusing on. And they lie within three sort of clear categories, and those are optimization, machine learning, and simulation problems. And that can be sort of, if we sort of break that down to like problems you may have heard of if you work in like the finance industry, portfolio optimization is a classic one that people are looking into right now. So optimization problems to try and build the best portfolios so that bankers can make sort of good options for their customers. And if we think about sort of the European energy crisis going on, large-scale grid optimization is a really, really complicated problem that even classical supercomputers today would find it difficult to solve. So these are exactly the sort of optimization problems we're hoping to look at using quantum. Simulation problems might be sort of the development of new medicines. They might be sort of building more efficient battery materials. And then a machine learning problem might be, for example, looking for anomalies or pattern classification problems with machine learning, and different things in that space as well.
Oh, sounds great. I mean, and I'm thinking of this hype we have today with AI, right? Putting quantum in combination with AI workloads will help, I think, boost solving some class of problem like the one you mentioned, and yeah, and maybe we can go also in this other point, which is okay. We quantum will solve this class of problem, but how we connect the classical computing to the quantum computing, and what is about how OpenShift is involved in all that, and we go to the maybe the audience was wondering, okay, I like this the physics behind, but what about OpenShift? What about today's Kubernetes?
So I think lots of the problems that Kate mentioned, the ones that fall into optimization and simulation, like an important part of many of these algorithms is that they have a classical part that runs. So part that runs on a normal computer, and then they have a part that runs on a quantum computer. And the way these algorithms tend to work is that they do some kind of optimization, and then they run it through a quantum circuit, and that loop goes round and round and round and round. And if you want to do that efficiently, if you want to get to a state where you're showing some kind of quantum advantage, you need to be able to do that really quickly. You need to be able to flip between your classical and quantum resources. And I think that sort of brings us nicely into like where OpenShift and these kind of technologies are important, because if you want to get that loop really quick, you need to have your classical resources right next to your quantum resources. And a big challenge of that is that you need to do this at quite some scale. We want good classical resources to utilize these quantum resources. And that's where technologies like OpenShift are really helpful to us, because we can run our classical computing right next to our quantum computing using OpenShift, and we can run that in a much more flexible way. And the way it tends to be is that load really varies as well. It depends how big the QPU you're using is, how many people are using it, what kind of job they're running. And the great thing about containers, Kubernetes, OpenShift for us is that it provides us with that flexibility at lots of different levels in our stack to scale more efficiently. And we use lots of auto scaling and these kind of things to help us deal with load and use that more efficiently. So that's really how OpenShift and Kubernetes play into the actual quantum data center itself. Yeah.
Okay, yeah, that sounds great. And I was thinking, Kate, you mentioned the quantum advantage. In the quantum advantage era, I'm thinking about a reference architecture. So that might be several components. There's could be, I don't know, maybe an OpenShift part for the classical computing, and then the AI part, and then the quantum part. Is that an accurate forecast of a possible common architecture for the quantum advantage? And how do you see the evolution for quantum? It's going to be always some hardware somewhere that you have to inquire via API, or it can also evolve in some more, smaller hardware and more distributed?
Do you want to go first, Will, or should I?
I know it's a tough question.
You jump in on that, Kate, because I think you've got something to say on that. Yeah.
So basically, I think like one thing that's super important to get is that like there's a hardware question here, but there's also a really, really big software question. So Qiskit, as we sort of mentioned earlier, like Qiskit is itself, it's a containerized architecture that sort of Will mentioned that there's part of the Qiskit software stack called Qiskit Runtime, which is the part I work on. And that itself is a containerized architecture that's working really, really close to the quantum hardware, as Will mentioned. That provides low latency access to all of our quantum computers. That's brilliant. But there's so much more to that. Like there's actually a huge software question there, which is how can, as you mentioned, Natalie, bring our users, sort of give them access to quantum hardware, but actually be able to look for quantum advantage in in the hardware that we have available today by making it as easy as possible to interact with these machines, but also in using classical computing techniques to make sure that people can actually get something useful out of these machines. So we actually have like a whole range of software questions where we're trying to use classical computing techniques to make it as easy as possible to interact with quantum computing hardware. And the main goal of that is that obviously in the end, we would like people that are not physicists and are probably, it's better if they're not physicists, to be interacting with these machines so that we can start to look at the industry applications and the applications that go way beyond just what the physicists find interesting. So we're trying to build a software stack that makes it as easy as possible to interact with these things, because obviously when software is done well, you shouldn't have to know what's going on under the covers in order to use it. Like, I have not got a computer science degree. I come from a physics background, and I do not care what happens after I submit my program to, I don't know, like some data center. Like, if I want to find out, that's up to me, but I shouldn't have to have that sort of barrier to entry like available to me if I don't want to achieve that. So what we're trying to achieve in the future is to build something called quantum serverless, which will give people sort of access to quantum hardware and build programming tools that make it as easy as possible to interact with this quantum hardware, so that people can start to build things without having a degree in physics or some other huge milestone that would mean that this technology is really exclusive. We're really trying to move away from that. So I'm not sure if that directly answered your question, Natalia, but I think there's a huge hardware question. There's also a huge software question, and arguably the software stuff is what's really, really of interest right now. Like, the physics associated with quantum computing was defined a long time ago, and there are huge engineering challenges that we're facing in terms of bringing that to life. But if you are interested in the software space, this is such a cool place to be working in right now, because the techniques that we're trying to build, and we can talk about more of those if you're interested, the techniques that we're using to make sort of quantum computing useful today for people and developers at home, that's such an interesting question on its own.
I like what you say, Kate, and this is music for my ears. You said software and developers, right? So we also have to focus on software. And about the software for quantum, I know Project Qiskit is an open source project, no? That have allow developers to try quantum in a kind of a simulation. How does it work?
Yeah. Well, do you want to do a sort of general intro to Qiskit? Or?
Yeah, sure. Qiskit is a software development kit. Like, in technical terms, that's what it is, and it's a Python software development kit, and it basically is a bunch of tools for using our stack and now other quantum computing stacks as well, that allows you to interact really easily with it. So you can, if you want to just create like a quantum circuit, which is like the way we write quantum programs, it's really easy with Qiskit. Like, it's quite straightforward Python. There's nothing too complex to do, and actually a lot of the like packaging around how you interact with our APIs, that's all abstracted away, so it makes it really easy for people to use our quantum computers and other quantum computers. And actually there's a lot of simulation features built in as well. So getting access to a quantum computer, you can do that for free with us, but actually, like, sometimes it's quicker just to run a simulation. At the moment, quantum computers can be simulated like up to a few qubits, and that's quite like easy to do with Qiskit. So it's a software development kit to allow you to do all those things, but it's also an open source community where you can meet other people who use Qiskit. You can contribute to Qiskit yourself, and you can go to events and learn from other people about quantum computing. Like, before I joined IBM, I used Qiskit and those resources loads to learn about quantum computing and to like get up and running with all the different concepts. And there's a textbook as well there that's free to use. So you can just log on and learn about those things there.
Thank you for this wrap-up explanation. And we have a comment in the chat. There's Marco say that TensorFlow is already one of the components for MLOps solution for OpenShift data science, hybrid quantum, classical machine learning, finding TensorFlow quantum, a candidate trade union. This is when we talk about how we connect the AI, the classical to the quantum. And he has a question also: shall we expect this kind of element to be integrated in MLOps on OpenShift? How will Kisskit operator fit in this picture? So he's asking how Kisskit will connect TensorFlow and and the MLOps offering. Maybe do you have already any idea in terms of architectural connection for Qiskit to MLOps?
I mean, I think probably I don't know directly about MLOps, but the so Qiskit's built in a few different ways. So you can, as Will sort of mentioned, you can build sort of gates and circuits to build your programs. But there's also another side to Qiskit, which is kind of more like I wouldn't say industry focused, but maybe specialism focused, which are these application modules. So we actually have a Qiskit machine learning application modules, which is basically a sort of layer that you can imagine that sort of separates the Qiskit software stack between sort of the tools that machine learning engineers might be already familiar with. I'm not actually sure, because I'm not a machine learning scientist myself, whether there's a direct sort of interface that's already been built for what you're describing with TensorFlow and TensorFlow Quantum, and whether there's already an integration there. But the machine learning application module is actually built for machine learning engineers so that they can integrate more easily with the Qiskit software stack. So if this isn't already in the roadmap, obviously sort of Will mention there that we are sort of the largest quantum computing open source software community available. And if you have a good idea, do check out the Qiskit machine learning application module. If something isn't already there, like by all means, like start a conversation with the community, see if anyone's already working on it, or even like raise a pull request yourself if you've got good ideas. I would imagine somebody's like maybe working on this field anyway, because obviously AI is such a bouncing field anyway, and like machine learning and MLOps is growing as well. So hopefully someone's working on it already, but I'm not actually sure if anyone has started. Will, please correct me if you know more.
No, I don't think so. I think it's a great question. I think I'll say that. It's a really good question. And I think as well, like the difference between quantum computing and classical computing and some of these things is that like quantum computing resources are different to classical computing resources. Like we have plenty of classical computing resources available to us, whereas we're always bottlenecked on there aren't loads of quantum computers. Like we have a lot, but you can't just build one, right? So it's going to be a slightly different model in some senses in the near term to classical computing in terms of like how you're able to actually run your code and those kind of things. I hope that makes sense.
Thank you, and thank you, Marco, for your question. And Kate, you mentioned, I think, an important thing, open source. We're talking about, a kind of a revolution for computer science. Again, after supercomputer and then the evolution for personal computer, whatever. Now we're in a new evolution. And you mentioned open source. So I think it's important putting open source from the beginning, right? Now that we understood the value of open source, and I really like that there's an open source project for quantum like Kisskit. And I was wondering, and I would like to ask you, what about this community around Kisskit? What are the people around this project? Are that physics or engineer or both?
Yeah, that's such a good question. I mean, so Qiskit originally started as just an IBM Research project that was built sort of as a Python-based SDK that people could interact with quantum hardware within the research community in IBM. But it's gone so much further than that. I mean, when Will and I were sort of chatting yesterday, being like, oh, what sort of point should we bring up? One of the jokes we made is that really this is a research project turned product. So quite a lot of our our software team are people that were there from the very beginning when they first made this just for an internal use. And then when everyone was like, hold on, why don't we make this open source? And I don't think anyone could have expected how big the community has grown to today. I mean, we have more than, I don't think 400,000 active users, but up to 400,000 people that have been involved at one point in time in our open source community. So it's an absolutely huge community, definitely the largest of its kind. And open source is absolutely core to making this sort of technology work, in the sense that obviously we mentioned earlier, there's a hardware problem and there's a software problem. With the software problem, like we are talking about a technology that's really only understood at like a high level and within a really small proportion of the global population of engineers and scientists and computer scientists, etc. So really we need as many people to be thinking about this technology as possible in order to ensure we're holding ourselves accountable from like an ethical standpoint, to make sure that we're holding ourselves accountable from like a scientific interest standpoint. From all of these different perspectives, we need people to be challenging us and people to be coming up with new ideas so that we can make sure that the technology is progressing as fast as possible, but also in a positive direction for the global community of interested people in quantum computing. And that's why open source is so key to that. So our software community extends far beyond just IBM now. The Qiskit community is absolutely massive, as I mentioned, and the people that are part of that community are from every kind of background. So I think, Will, correct me if I'm wrong, but like my experience so far is that we've got a lot of students that are like, it's absolutely brilliant to have them on board, but we also have a lot of people from industry who are interested in more sort of the application side. The students might be more interested in either sort of the computer science or the physics side or other places. But then we've got sort of just the general public as well that are like, can we use it for this? How about we try that? And that is like every corner of those sort of different groups of people helps to make this community so interactive. We have hackathons, we have events.
Oh, nice.
We've never sort of, I think it's constantly growing. There's never been a lull. It's always been a really, really interactive community and a great place to work. And if anyone's interested, I'll also post about our advocate program, which obviously is a great program to meet these people and to get invited to these events. But also it's on the online community. They all work via Slack. And I think if anyone has any questions about even learning quantum computing using Qiskit, or using Qiskit to program your first circuit, or to build your research project for your master's thesis, everyone is contributing there and will be happy to answer any questions you have. Will, I don't know if there's anything to add to that.
No, not very much. I just think it's like, if we're trying to build something frictionless for everyone to use from lots of different industries, like making it open source is like absolutely essential, because we've got lots of expertise in IBM on hardware and various bits of the software stack, but we don't have expertise on, you know, every single industry, and it's like really like integral to the mission and helping quantum computing get adopted more widely. So yeah, definitely.
I love it. I just shared in the chat the link. Thank you, Kate, for sharing it, the Advocate program. So I'm going to subscribe myself. I'm really interested. I want to learn about quantum. I want to join the Slack channel, and I want to be, and I really recommend also you to do the same, because you can join those events, you join the community. It's a really cool program. So thank you for sharing it with us. Connect with those enthusiastic advocates for the this beautiful Kisskit community that, as you have heard, it touched many people, from students to professional to just passionate. Everyone is there. So thank you for sharing it. Hey folks, you know what? This show is a live demo show usually. Do we have anything to show to the people they can touch and see?
Yeah, sure. I think Will's got something prepared.
Yeah. I'll just go through something. It's not going to be big on quantum computing. It's going to be big on how you access our resources.
No, I was expecting you had the quantum computing behind you, and you can show us how it.
Here's one I made earlier. Unfortunately, not. I haven't got to that level where I've built my own yet. Right. So yeah, I'll just try and share my screen. So something we're passionate about is people being able to use quantum computers for free, or at least some of them. And anyone can come to quantumcomputing.ibm.com, which is where I am now. Can you see my screen? Is that all good?
Yes. Yeah, we can see.
Cool. And you can use our simulators for free. So we have some cloud-hosted simulators. Again, another shout out to OpenShift and Kubernetes there. And you can also use some of our real quantum backends here for free. And you can do this in a couple of ways. So this is called the Circuit Composer, which I'll just show a little bit about today. But then on the right here, you'll actually see this is Python and using Qiskit, writing out the code that I'll be doing here. And you can also use Jupyter notebooks as well. So if you get a bit more advanced, like this is a great place to come if you just want to try some little things and see what happens. But as you get a bit more advanced, you might want to use Jupyter notebooks. It's just a bit more of a scalable way of writing your code. You'll see that as we get to a few qubits, it might get a bit clunky here. But Kate talked earlier about qubits. So this is called a quantum circuit, what we're looking at here, this middle bit. And this Q0 is sort of a wire going left to right, and this represents our qubit. And then C1 is our classical register. When we do quantum computing, we measure classical bits. We can't measure in a quantum way. Like we either measure 0 or 1 for each qubit when we get to the end. So I'll just show like a simple circuit. and then show how it can be run. And then hopefully that's enough just to get people started. And then there's tons of resources out there to learn more beyond this. So by convention, when we have a qubit, we start in state 0. So if I add this thing, this is called a measurement gate. So in quantum computing, we use these gates to show how we're manipulating our qubits. So this is our qubit, and by convention, it starts in state 0, and we measure it, and the output comes to this classical register we have. And you can see here, we just get a quick preview of the result of this circuit. And you can see that we are always measuring 0. So that's good news. That behaves as we expect. And then we can do some things. So we can do classical computation on quantum computers. So this gate here is essentially a bit flip. And what this will do is just take us from state 0 to state 1. And at the moment, this is running through a simulator, so it works absolutely perfectly. So you can see that we start in the 0, we flip to state 1, and then we make a measurement, and we measure 1 every time, which is good news. So that's just sort of a classical computation we can do on a quantum computer. Things start to get a bit more interesting and a bit more quantum when we introduce this thing called the Hadamard gate. This is definitely like one of the more special gates in quantum computing. It's one of the building blocks. And now you can see more interesting things happened. You can see down here, after we use our H gate and then make our measurement, you can see half of the time we measure 0 and half of the time we measure 1. And that's because we've gone into this thing called superposition, which Kate talked about. And actually, in this case, it's really simple to sort of see what's happened. Half of the time we measure 0, half of the time we measure 1. It's quite straightforward, really. Things get a bit more interesting when we introduce a second qubit. So we now want to make a measurement on that second qubit. So you can see how you can just drag and drop gates in as you like. And we can then use a thing called a CNOT gate. To what's called entangle our qubits. So here we've kind of got a lot of quantum computing in a very simple circuit. So the CNOT gate, essentially, the value of this second qubit which we've introduced depends on the value of this first qubit. So if this first qubit is in state 0, then we don't bit flip, and if it is in state 1, then we do bit flip. But because we've used this H gate and we're in some superposition state, you begin to see things get a bit more complicated. I won't go too deep on the maths for now, but hopefully you can see how some more strange things begin to happen. And actually the output of this circuit is 0011. So this means that half of the time, so we run this circuit lots of times, this simulates having run it 1,024 times. Half of those times we'll measure both qubits in state 0. So we'll measure a 0, we'll measure a 0. Half of the time we'll measure 1 and measure 1. But we never measure these middle states. So we never see 0 and 1 on the other, and vice versa. So don't worry if that was a bit quick. The point here is really just to show you how to use the composer. If you want to run it on a real quantum computer, you click on that button on the top right, set up and run. And then here you'll see a list of devices that you can use. Some will have a little queue. This is just a simulator, and it can simulate up to 32 qubits, and I can choose how many shots I want to do, how many repeats of the circuit, and then you just click run, and you get the little spinning running, and then you can come over here, and you can see it's currently running, it's currently in the queue. And because we're running on a simulator, it should be fairly quick. We might have to wait for the result. We might have to come back.
No problem. I think I can, Will, I can share in the chat the link for the people if they want to try themselves. This link, quantumcomputing.ibm.com. And Kate also shared with me a very nice tutorial to build your first circuit. I think it was really similar to what you showed today, right?
Yeah. So using those same sort of Hadamard gates to introduce superposition and those same CNOT gates to introduce entanglement. So you're getting your physics lesson hands on.
Amazing. So this is kind of all the people can try it for free, as you did.
Yep. You just you have to make an account, and then you can use it for free. Yeah.
Wow. And usually you have a list of either simulator or real quantum computing, right? Computers where you can send the workload.
Yeah. So when I clicked on that setup and run, I've limited mine slightly so that you don't see all the internal ones. But there you'll see a list of ones that are freely available to use. And if you can click on it and you can click run, then you can use it, kind of thing. So and it will, yeah, there'll be up to 7 qubits on real quantum computers that you can use at the moment.
Wow. Yeah, this is exciting because the people can really try themselves. And what is this connected to Qiskit, or is just an interface to something else?
Yeah, I mean, you might have noticed that on the right-hand side, I think it was right for me, on the right-hand side of Will's screen, you could see some Python code being auto-generated as he was dragging and dropping the gates. The alternative, Will, I'm not sure if you want to just show what a Jupyter Notebook looks like and how you can access it from that UI. But you can do everything we were doing using the drag and drop gates in Python code if you're more comfortable with that as well.
Oh, cool. Also Jupyter Notebooks?
Yeah, I think, Will, are you able to flash them up?
It's just loading. 1 second.
Nice.
We're incoming.
Yeah, so on that same user interface you'll land on when you type in quantum-computing.ibm.com, you'll have an option to start the composer or the lab. If you use the composer, that is the drag and drop interface that Will was just interacting with, but then the lab is the Jupyter lab that does spin up. So hopefully that will be ready in a moment so we can show you that.
Here we go. Right. Cool. Okay, so this is what the Jupyter notebooks look like. Here's some stuff from an old demo I did. You essentially, what I've done is you go to the menu and then you click on Quantum Lab and it will bring you to this landing page. And when you open that, you'll get some, there's some resources in here already. So you can go in the tutorials and it will talk you through how to write various circuits and these kind of things. Or you can open a new notebook and you get some sort of boilerplate stuff, which just means you don't have to worry too much about the setup. It just makes things a bit easier. You might have to do a bit of tweaking there depending on what you want to do, but if you can write a bit of Python, it shouldn't be too difficult to get started. And then you can see here, like, you construct a quantum circuit, is what I've done here. So, and then I've added some gates in, and then I've added some measurement gates in. And then you can do this thing called qc.draw, which is super handy, and it gives you a nice diagram back. And then you can actually run this on a back end. So then you actually need to execute this on a back end. So I've just chosen the simulator here. And then we print a nice histogram of our results. So it's just a different way of visualizing the same thing. But for simple examples, it shouldn't be too much of a leap.
Nice. This is super cool. I mean, there's also this editor where you can edit the code from here. I love it. And yeah, and I was also looking, when you want to install Kisskit in OpenShift, you have the operator, right? You can, in your OpenShift cluster, usually you can install the operator by looking into operator hub, marketplace. There should be the operator provided by Red Hat, the community one. And I was going into, if you want to try yourself, I think you can all go here. Let me share this link in the chat. We have this learning portal in our developer portal. And I can show to the people how it works. Let me quick start sharing my screen. If you want to try it out yourself, right on, should be this one. So if you go to the learning portal, you can go, this is the Red Hat developer learning portal. We have a list of our OpenShift labs that you can try for free. Maybe Kate will. We can add one for Qiskit here, and if you are interested, we can add to this offering also the Qiskit lab.
Awesome.
It would be nice, right? But for the people that want just try it out, I think you can go to the playground. I already started. The playground is an empty OpenShift cluster. I already started it one. I'm here. So you can go to the web console. It starts immediately because we have some kind of a hot start. And you have
Natalia, we're looking at your YouTube page. I think we might need to switch to your other screen.
Oh,
we've now got sort of the matrix of.
Yeah, sure. Sorry about it. What I'm doing here, I'm showing. I was showing stuff for. Sorry about it. Let me share the right one. So the window is this one, not that other one. Right on. Is that better now?
Now we're looking at your tabs. Yeah, perfect. We're there now.
Right.
That's it.
Sorry about it. I was showing. Hey, you want to install Qiskit on OpenShift? You go into Operator Hub and you look for operator for Qiskit. You have the IBM Quantum operator to install it, and you have the Qiskit playground. And if you have, I was showing that if you want to try now, you can go to Learn, which is our learning portal on the developer portal. If you go to this page, I put the link in the chat. You go here, and I was saying, hey, maybe we can. We have a list of OpenShift labs over here. Maybe we can add one for Qiskit in this page. It would be nice to have one lab that you can start and try from this page. This is a cloud OpenShift instance that will start, but right now you can also start with an empty OpenShift cluster. This is an OpenShift 4.12. This start, and then you can go into the web console of your OpenShift cluster, log in with the credentials that are in the lab, and you can start installing Qiskit operator over here if you want to try yourself. And Kate will, I was looking for into Operator Hub for Qiskit, and I have this Qiskit playground. So basically, I just clicking install. This is going to install the operator in the cluster, and then you can, I suppose that you can start trying your Qiskit workloads in OpenShift. So it's easy to get started with the operator because it provides all the API to start working on OpenShift with Qiskit, and then you can follow Qiskit documentation and tutorials to really run your workload. But as you can see, it's really easy to start with Qiskit operator, and you can start with our learning portal if you want to start it right now. So you have basically, let me stop sharing my screen. You can try yourself Quantum with the IBM Quantum website, and also you can try on OpenShift Qiskit with the developer portal.
Yeah, and I think that should pull up a really similar Jupyter notebook to what Will had on the screen once the operator is installed as well.
Yeah, sure. Yeah, I love it, and this is amazing. And yeah, sorry about the cascading YouTube. I was talking for minutes nonsense. Sorry.
No, it looked really cool.
Some effect. Yeah, I'm really excited. Hey, folks, if you have any question for Kate and Will in the chat, please let us know. We will bring this question. I think today we've seen a really cool stuff to get started with Quantum and Qiskit. Maybe again on Qiskit. What are the typical use case for Qiskit? If I have my OpenShift cluster, what I can do with Qiskit useful?
Yeah, no, that's a really good question. So I think probably the most used, I think lots of people are jumping on the website to get started and to learn. So lots of people learning quantum computing are definitely jumping onto the Circuit Composer to see how, I think like, for example, the demo Will showed there, it's a really good way to actually visualize what we mean when, like, quantum is all about probabilities. So we live in a deterministic world where I'm sat in front of my TV, in front of my laptop screen right now, and I'm talking to you guys. in a quantum world, everything's a bit probabilistic. So I've got 50% probability of being here, 50% probability of being somewhere else. So that's sort of actually visualizing that on the histogram that Will showed. It really kind of brings to life these concepts like superposition that we can talk about, but it's nice to see. So definitely lots of people jumping onto the Composer tool to learn more about quantum computing. I think from like more of a research and people like actually using it for their work, it's a bit of a mix. We have those application modules I mentioned, and I think there's currently 3 of them. There's an optimization application module, which has loads of sort of inbuilt tools for building optimization applications and different sort of workloads there that are related to optimization. And I mentioned the machine learning application as well. And we also have a finance application, which is specifically for, particularly because we have such a large community of sort of financial services industry users and people working in that industry. We do have a specific financial services application module, which is made up of both kind of optimization and machine learning tools in there. So under wraps, a lot of that is replicated in the optimization and machine learning application modules. But probably lots of people coming in to use those application modules, and then people coming from a research perspective as well, where the circuits are a bit more bespoke to their research. Will, anything else that you'd add there?
No, I was just going to say you can go super deep as well. You can go all the way down to the pulse level. Like the way quantum, our qubits are controlled is microwaves that come in and change the frequency of oscillation of the qubits. And you can literally go right down to that level as well. So like Qiskit is the full stack. It's whether you know tons about physics and that's really what you're into, or whether you're like working at a very high level and actually you just want to optimize something and that's all you want to do. So it goes across the whole sort of spread.
Nice. Thank you for this clarification. Really help understanding, the people that want to use it for any particular use case. They can try themselves. We have seen how easy it is to get started with Qiskit with the operator on OpenShift, available from Operator Hub, and this wide community. Hey, is there any next conferences about Qiskit, or will be the Quantum Summit, the one?
I think so Quantum Summits are a big annual one. There should be quite a few events in between now and then, though, that hopefully there'll be some information for on either the Advocates website or just the general Qiskit website. Because the Qiskit community extends far beyond just IBM, they tend to operate a lot of events on their own. I know they have weekly seminars as well, so if you're interested in learning more, you can tune into the seminar series that they can send invites to you about. And you don't have to be an advocate to join those. You can join those just as an interested person as well. So definitely lots of virtual stuff to join. And I think there should be some in-person events too that hopefully are visible on the Qiskit website somewhere.
Mm-hmm. Thank you. Yeah, definitely exciting. I'm excited. I'm convinced. Do you have any final words for us? Any things you are excited about it, about quantum and about evolution? Anything you want to say to close this really cool episode?
Maybe I'll jump in. I think if you're like, I'd say if you're interested and you want to get like if you're interested but the concepts are a bit much, like just go on and like have a go, because for me like that's the way I learn. Go on and have a go with those things, like try out the tools, and like even if that's where you leave it, like it's a good way of getting a better understanding. And like it's a great time to like learn a bit about quantum computing, because it's definitely only going to grow and get bigger. So like it's a good thing to understand if you want to go and do that. That's what I'd say. Yeah.
So start learning. Just start learning. You have plenty of resources. You have the Qiskit website, the quantum computing website with the tutorials. I guess there are also other tutorials, right? Not all the circuit one. There are many ones available. Yeah. So those are the first step. Is the Slack community active? The people want to chat and learn.
Yeah. Super active. So yeah, if you are interested in getting involved with the Qiskit community, there's a separate sort of Qiskit Slack space you can join, and it's super interactive. I'm getting tagged so many times a day from there. Just people are very, very active in that community.
Amazing. Well, with this, really thank you, Kate and Will, for joining us today. It was a really exciting and interesting episode to learn more about quantum, the physics behind the engineering aspect, but also, as you mentioned, Kate, the software and open source aspect of it, and what are the possible application on OpenShift. Was some comment in the chat how we to mix and connect AI workloads to quantum workloads, more interoperability for the upcoming future. I see, right? Something like that. And if you want, hey, Kate, Will, do you have any Twitter handle you want to share with the audience if the people want to follow and know more about you and
Yeah, sure. And also feel free to reach out on LinkedIn if anyone's on there. I'm more active on there than I am on Twitter, but I will also share a Twitter handle.
Yeah, please share with us your social if you want to connect with Kate and Will. And you are part of the advocates program, I think, right? So if you join that program, I think you will get in touch with them. Before we close, some quick reminder: we will come back next week with OpenShift Coffee Break. But today we also have more episode in our US time frame. So stay in touch with us on OpenShift TV, and we come back the next week for another episode. Let me look at what we have in the agenda, and let's check quickly. So we have our partner Portworx Pure Storage talking about data, the DR and business continuity with Portworx and OpenShift. So this is for today. Really thank you, Kate, Will, for being our super special guest at OpenShift TV. I hope to see you soon for our next update on quantum. And hey, folks, please go to the Slack channel, join them, the Qiskit community. Really exciting times ahead towards the quantum advantage, right?
Yeah, exactly.
Thank you.
Thanks so much for having us.
Thank you. A pleasure. Bye.
Bye.